of this video is to review some logical implication or logical consequence. This could be something that shows up on your tests, and some people were wanting a video on this. We did cover this on Thursday's lecture, and there are a couple examples in the slides. So this is saying, roughly speaking, that there is something that is both a P and a Q in the universe. And we're saying that this logically implies that there's something that is a P in the universe, or for everything in the universe, if it is a P, then this same something that was a P, or it could be a P, is a Q. And this kind of translation here is atypical, as normally this would be a QX, or it would have X in it somewhere. Maybe if this was a binary predicate, it would have like QXY. Having no X in there is a little atypical. Okay, so we're going to walk through our steps on how to show that we have a logical implication in first order logic. So the first thing we need our interpretation. So we're letting I be an interpretation such that our premises are true. You might have more than one. Right now we just have the one premise. And as you can see, we are setting our premise to true. Now, once we've set our premise to true, these proofs kind of mimic how natural deduction proofs work. Here, we're going to probably want to peel this off and use the semantics, use the meaning of existential quantifiers. Well, what does it mean? It means there's something in our universe that makes this true. So, remember, we have been assuming that our universe is non-empty. And so assuming this by our existential semantics, so the meaning of this quantifier here, we know that there is some item in our universe that sets this to true. We don't know what A specifically is. We are just saying that A is the element that makes it true. A is whatever the one thing that makes it true. And again, there could be more than one, but there's at least one, and we're just giving it the name A. So now that we have that this is true, we can see that the next step is to make use of the conjunction. So by the semantics of conjunction, we know that if this is true, then this has to be true, and this has to be true. You know, just like in propositional logic. And so here we have, in the interpretation, this is true, and QA is true as well. Now, we want to look at our conclusion here. Our conclusion here is saying we're existing a Y. Now, this exist could be added in afterwards. Not every way is going to work that way. And remember, when in doubt, try a proof by contradiction on the test. So here we have PY or this. And we have PA, and we know we're going to put an existential quantifier that matches whatever this variable is here. So we know already that there's an item that satisfies P, right? It's A. And so all we have to do now is to introduce our disjunction, and then we can do the existential quantifier. Now the trick with this is that we need this value to be the same value as here. So we're going to introduce this part here, but this value is going to match this value, and in this case it's A. So we're going to use the semantics of disjunction, and then you can see here we have the PA, or we put this part here, but we replace the Y with A. And we're saying that since PA is true, then PA or for all x P of x implies Q of A, that's true. So since this is true, we know at least one of these is true, and we definitely know it's this one. So now we can see that the last step is that we want to introduce the existential quantifier. And since there's something in our universe that sets this to be true for where we want to put the y's, then we know if we had y and y mapped to that item in the universe, then the statement would be true. So since A is an item in the universe, if we had put the variable y instead, then when y maps to A, this is true. And since A, again, is an element in the universe, and by existential semantics, which means there has to exist something in the universe that makes it true, we get our result, which is that this is true under the interpretation. And then we do a closing statement, and it's whenever I sets my premises, or in this case there's just one, to true, my conclusion is also true. Therefore, we have exists x, p of x, and q of x logically implies exists y, py, or for all x, if px, then qy. Because remember, this here is the definition of this. And we didn't pick I to be a very specific interpretation. We just let it be an interpretation that made our premises true. If I is an interpretation that makes our premise false, well, we don't care about that because false implying anything is true. The only time that this is ever going to not work is if we had an interpretation that made our premises true but made our conclusion false.